Hello, I'd like to welcome you to today's presentation about the development of a hardware SAR-Monitor for a neonatal MRI scanner. My name is Jochen Suchmann, and this project was part of my master studies in medical systems engineering at the Otto von Guericke University Magdeburg. Before I talk about the development itself, I'd like to give you a short introduction on this topic and point out its importance. In 2018, there were 4 million deaths of children under the age of 1, whereby one of the main causes were untreated brain injuries. In order to be able to treat them, they must be diagnosed. Therefore, neonatal imaging is essential. The most used imaging modality for these diagnoses is the magnetic resonance imaging. Nevertheless, there's no ionizing radiation necessary. In MRI, still high-power magnetic fields are needed. They are used to excite the magnetic moments of the water molecules. The de-excitation of the so-called spins is measured by coils and used to reconstruct the corresponding images. In order to excite the magnetic moments, electromagnetic radiation has to be used. The electrical component of this radiation cannot be used for imaging, but results in heat generation within the patient. This heat cannot be measured directly, so in order to give a measure, the International Electrotechnical Commission established the specific absorption rate, being basically the electrical field power to the patient. The SAR is limited by the corresponding standard, and by adhering to this norm, no critical heat will be generated within the patient. The electrical field in the patient can also not be measured directly. Therefore, electromagnetic field simulations can be performed calculating the electrical input power to the transmit coil and the corresponding limits. This electrical input power limits can then be used in a hardware SAR-Monitor, which measures the actual input power and compares it to the limits. If any limit is surpassed, the RF power to the patient is interrupted. For this specific SAR-Monitor, certain requirements were stated prior to the development based on the corresponding standard and the available system. The maximum power is 200 watt continuous wave and 2000 watt peak, due to the RF amplifier in use. The frequency is 61 to 63 MHz due to the 1.5 Tesla system. In order to resolve the pulsed RF signals, a sampling rate smaller than 10 microseconds is necessary. Based on the IEC 6061-2-33 standard, the limits are stated as 10 seconds and 6 minutes means. Therefore, the SAR-Monitor must calculate those means, and the overall error should be below 5%. The hardware SAR-Monitor can be subdivided in individual SAR monitoring units, placed in the transmission line of the RF chain. All units combined are the complete SAR-Monitor. Each SAR monitoring unit consists of a dual directional coupler, which transforms the high power RF signal into a low power RF signal. This low power RF signal is converted into an analog low frequency signal by an RF to DC converter. The analog low frequency signal is digitized by an ADC, and the digitized data is further processed by an evaluation unit. Based on this computation, a blanking logic disables the RF amplifier in case of an error. Each of these components must be evaluated precisely in order to maintain low errors of the overall system. Following, I will describe each component individually to give an overview of their functionality and their performance. A dual directional coupler fulfilling the stated requirements is the IPP8044. Dual directional coupler use electromagnetic coupling between a high power line and a measurement line in order to convert a high power signal into a low power signal. So If a high power signal is going from port 1 to port 2, it couples into port 3 and port 4, whereby port 3 is the intended measurement port and port 4 is the non-intended isolated port. When a signal goes from port 2 to port 1, it is the other way around. For the dual directional coupler, it is important to have a low reflection at its input and as low as possible absorption in the coupler itself. Since the IPP8044 is only used in as a directional coupler, only the data in one direction is shown. It can be seen that the reflection part at port 1 is below minus 20 dB, which means that less than 1% is reflected at the port 1. The absorption is below minus 0.02 dB, resulting in less than 2% of absorption in the dual directional coupler. The intended coupling is around minus 50 dB, but varies from coupler to coupler. The isolated port is coupled by around minus 70 dB, which is close to isolation and does not affect the measurement itself. This data shows that the dual directional coupler is suited for this application, although the coupler vary components specifically. The next component of the measurement chain is the RF to DC converter. One fulfilling the requirements is the ADL5511, which is a linear RMS to DC converter. This component must be evaluated precisely since its characteristics will affect the precision of the SAR-Monitor. The characteristics are used within the evaluation unit to recalculate the actual RF power based on the digitized converter's output. The characteristics of 8 converters are obtained by applying a specific power to the input measuring the output. The graph shows a strong linear behavior for power above minus 10 dBm and less linearity below. In order to be able to perform the recalculation, a linear regression is performed, displayed by the drawn lines, whereby the crosses show the measured data. The results are displayed here. So the output voltage is linearly dependent on the input voltage. Therefore, using this formula, the input power can be recalculated based on the output voltage and the regression parameters displayed in this table. It can be seen that all parameters vary from component to component and they especially differ from the values given in the datasheet. Not using the correct parameters can result in up to 15% variation on the calculated power. Therefore, a precise characterization is essential for low errors. The R-square value, as a measure for the goodness of fit, shows that the regression fits to the data quite good, since 1 would be a perfect match and 0 would be no match. The next component is the ADC and the evaluation unit, which is realized on an MSP432 microcontroller. The software is organized in a finite state machine like displayed here. There are 2 finite states, communication and sampling, and 2 events, sampling start and sampling interrupt. When in communication state and the event sampling start occurs, the state changes to sampling and the RF is enabled. When in sampling state, the event sampling interrupt and the event sampling interrupt occurs, the state changes to communication and the RF is disabled. The communication state is organized in an infinite loop, where interrupts are used to trigger every time a new command is received. After information about the baby and the corresponding limits is transmitted to the microcontroller, a start command will result into a state change, which results into the sampling start. If any information is missing or wrong information is transmitted to the microcontroller, the state will remain and an error message will send back to the host computer. The sampling is also organized in an infinite loop, in which the ADC data is read in and the input power is calculated based on the ADC data. In parallel, the 10 seconds and the 6 minutes mean are calculated, and it is repetitively checked if a limit is exceeded. Furthermore, a peak detection is performed as well. Every time a limit is exceeded or a new command is sent to the microcontroller while sampling, the state changes to communication. It is important to know how fast the sampling is in order to be able to check if the requirements are fulfilled to sample below 10 microseconds. Therefore, a toggle function is placed in the infinite loop directly after the ADC read function. Here it can be seen that every 7.56 microseconds a new value is received by the microcontroller, so the requirement is fulfilled. Additionally, it is checked how fast the peak detection is and how often the 10 seconds and 6 minutes limit exceedance is checked in the same way. The result is that the peak detection is performed every 7.56 microseconds likewise. The 10 seconds limit exceedance is checked every 40.4 milliseconds, and the 360 seconds exceedance check is performed every 10 seconds. In order to evaluate whether the mean calculation works properly, the limit is set to half the input power. For the 10-second mean, it can be seen that the limit is exceeded exactly after 5 seconds, and the 360 seconds limit after 168.4 seconds. So considering that the 360 seconds check is performed every 10 seconds only, it can be said that the mean calculation works properly. The last component of the SAR-Monitor unit is the blanking logic, which adds a software surveillance to the SAR-Monitor by using a hardware watchdog. This watchdog's input is toggled by this toggle output of the microcontroller during sampling state. If the software freezes, the watchdog sends out a low pulse. If any of the limits is exceeded, or the state is changed to communication, the error output of the microcontroller goes low. If any of the inputs of the AND gate goes low, its output is set low as well. This will result in a set flip-flop, which will disable the RF. This can be only undone by manually resetting the flip-flop using the FF reset pin of the microcontroller. So it can be seen that each SAR monitoring unit is connected to a lot of work in setting up and characterization in order to guarantee a precise performance. Therefore, it is checked whether SAR monitoring units at all 4 positions are necessary. To serve the purpose, a 1 watt RF signal is applied to the input of the RF chain, and the forward and reflected power at all 4 positions is measured for an enabled birdcage and a disabled one. For an enabled birdcage, the displayed power was measured. It can be seen that around 75% of the initial power goes into the birdcage and 25% is lost in the quad hybrid. So what can be said is that measuring the power only at the P-in with knowing the losses within the transmission line can be used as an upward approximation of the power to the patient, which results in that I and Q positions could be saved. When disabling the birdcage, a major error at the birdcage is simulated. It can be seen that the power to the 50 ohm dummy loaded increases significantly. Since the means at this position are not interesting, a peak detection at this position would be sufficient to detect a major error at the birdcage. Using these informations, the resulting final SAR monitor looks like depicted here. There are 2 dual directional coupler, 2 RF to DC converter, 1 evaluation unit with 2 ADCs and 1 blanking logic, whereby For the power measured here, only a peak detection is performed, and for the power measured at this position, the two limits, the two means are calculated and the peak detection is performed. Basically, 1.5 SAR monitoring units are sufficient for a minimal version of a SAR monitor. This final setup must be tested under the high power conditions. Therefore, the power was measured by a network analyzer and a SAR monitor, and the measured power difference between those two measurements was below 1%. Next, the 10 seconds limit was set to half the measured power, and the time until the limit is exceeded was measured. It can be seen that it took 4.96 seconds, which results in an error of 0.8%. Finally, the peak detection is tested. Therefore, at some point the birdcage is disabled. It can be seen that the error output is triggered almost immediately, indicating a functional peak detection. In conclusion, it can be said that a fully functional SAR monitor with an error below 5% was developed. A 15% safety margin on the SAR limits will result in a safe procedure. Nevertheless, the dual directional coupler and the converter characteristics vary component specifically, resulting into time-consuming measurements. Here, an automation would be beneficial. The microcontroller works at maximum speed, so it should be considered using a more powerful one. But in conclusion, a first prototype of a fully functional SAR monitor fulfilling the normative requirements as well as the technical requirements was developed. Thanks for your attention, and you will find the corresponding citations here. If you have any further questions, feel free to contact me under yours.hubmann@st.ofgu.de.